Hi, my name is Nabil Koinomizi, ID number 220000968.
Hi, my name is Muhammad Faris Daniel, ID number 2200135.
Hi, my name is Muhammad Daniel, ID number 22005995.
Hello, my name is Arisha. My ID number is 22002898.
My contribution to this project was finding the relative permeability using Corey relative and Broc Corey permeability models. I've also edited the video for this project.
My contribution to this project is change the capillary pressure to relative permeability using Burden approach.
My contribution onto this project is I will explain about capillary pressure, how it is measured regarding to Purcell approach.
My contribution to this project is finding the relative permeability from capillary pressure by using Purcell relative permeability model.
So, the capillary pressure means the pressure difference between non-wetting and wetting phase across their interface in a porous medium. It rises due to interfacial tension forces. So, how we measure this capillary pressure? There are three methods, which is first one is centrifuge method. The sample is subjected to increasing centrifugal forces simulating different capillary pressure. The second one is we use porous plate method, which is the sample is placed on a porous plate with a controlled pressure difference across it. And the last one is MICP method. The non-wetting phase is injected into the sample, which is we use mercury, and the pressure required to displace the wetting phase is measured.
So I'm going to talk about relative permeability. Relative permeability is the ratio of the effective permeability of a fluid phase in a porous medium to absolute permeability of the medium. It is represent the reduction in permeability due to the presence of other fluids. Relative permeability can be measured by direct measurement, but is very challenging. Instead, it is typically determined indirectly from capillary pressure data and core flooding experiment. For core flooding experiments, oil and water are injected into a core sample under different flow rates, and the resulting pressure drop is measured to calculate the relative permeability. And then for estimation from capillary pressure data, this involves using empirical models and numerical simulation to estimate relative permeability based on capillary pressure curve.
So first of all, capillary pressure and relative permeability is important to describe the behavior of multi-phase flow. Okay, there are different properties, but they can be interconnected, so we can find relative permeability from PC curve. So first of all, from PC, so we can use Purcell approach to find the relative permeability. So KRW is the relative permeability for the wetting phase, and KRNW is the relative permeability for non-wetting phase. So in our case, our wetting phase is water and non-wetting phase is gas. So first of all, for every capillary pressure that we got, we must find the relative permeability. So the SW is the saturation at that pressure. So we find the KRW for each pressure, and then we plot. And then for the non-wetting, we use the same formula. The SW is the saturation at that particular capillary pressure. And then we plot both of these for the relative permeability curve. And then we move on to Burden approach. So for Burden approach, it is almost similar to Purcell approach, but we add tortuosity square and then we times the formula for Purcell approach. So how to find tortuosity ratio? For tortuosity ratio, for the wetting phase, which is the water, this is the formula. So the SW is the saturation for each pressure, and then the SM is the minimum water saturation or the wetting phase saturation. So the minimum water saturation is the residual water saturation. So we find the formula by tortuosity ratio for the wetting squared, and then we times the formula, which is the same as the Purcell approach. And then for the non-wetting, it is similar, so we must square the tortuosity and then times the Purcell approach formula, but we must take into account the SE. But the SE we assume it is 0, so SE is the equilibrium non-wetting ratio. And then we move on to the Corey relative permeability model. So Corey relative permeability model, it is easier than both of the methods before because they didn't use any integration. So first of all, we must find the normalized water saturation. So the normalized water saturation, we take into account the wetting saturation for each pressure, and then we minus the residual water saturation, and then we find the normalized water saturation. And then to find the relative permeability for the wetting phase, it is normalized Q. And then for the non-wetting, it is 1 minus normalized square, and then we times 1 minus normalized square. And then we got these two relative permeability. We plot against the SW fourth method, which is the Broc Corey relative permeability model. So first of all, the PC is the capillary pressure for each saturation, and then PE is the threshold capillary pressure, the normalized water saturation, and power of negative 1 over lambda. So how do we find the lambda to use in the equation? So we must plot a linear graph for ln PC, ln PE, and then 1 minus lambda. So 1 minus lambda is the gradient or the slope, and then we can find lambda from there. And then for the relative permeability, so it is the normalized water saturation, and then 2 plus 3 lambda over lambda for the power. So this is for the wetting phase, and then for the non-wetting phase is 1 minus normalized water saturation square, and then 1 minus normalized water saturation 2 plus lambda over lambda for the power. And then we move on to the last method, which is the Purcell relative permeability model. So it's almost similar from the Broc-Corey, but we doesn't have to square it. Okay, so first of all, for the wetting phase relative mobility, so we use the normalized water saturation and then the power of 2 plus lambda over lambda. And then for the non-wetting phase saturation, which is the gas saturation relative mobility, we use 1 minus normalized water saturation and 2 plus lambda over lambda for the power. Then this is the results that we get for every KRW and KRG, which is the relative mobility for water and relative mobility for gas. So for each approach, we plot this against the water saturation. So based on the results, we can see that for KRG that we get from every graph, it is higher than the experiment value. And then for the Purcell approach and Purcell model, the relative mobility for the gas is different and it is erroneous. So it is not suitable to be used because the graph is not the same for the relative mobility. And then for KRW, for each method, for the Broc-Corey, it is slightly lower than the experimental results. And then the most accurate and the most close to the experiment result is the Bourdin approach and the Corey method. And then we have larger and higher value for the Purcell approach and the Purcell model.
In conclusion, capillary pressures and relative permeability are critical properties in the study of multi-phase flow in porous media. Capillary pressure resulting from surface tension forces describe the pressure difference between the non-wetting and wetting phase. It can be measured using methods such as the centrifuge, porous plate, and also mercury injection capillary pressure. And also, relative permeability quantifies the reduction in permeability of a fluid phase due to the presence of other fluid and is often determined indirectly through core flooding experiments or estimation from capillary pressure data. The relationship between capillary pressure and permeability is complex and depending on each other, with various models being used such as the Purcell, Bourdin, Corey, Broc-Corey, and Purcell relative permeability model. These models were developed to describe their interaction and also to understand these properties, and their connection is crucial for predicting and managing fluid flow in porous media.